Question 4 says a vehicle has a mass of 1,250 kilograms and a suspension system with a combined stiffness of 50 kilonewtons per meter and a loss angle of 20 degrees. The vehicle is driven over a road which gives a vibrational input which can be characterized approximately by a constant spectral level of 0.001 g squared per hertz. Find the root mean square vibrational acceleration level of the car. So, we've got M is 1250. We've got a K that's been given as 50 kilonewtons per meter squared, so that's 50 times 10 to the 3 newtons per meter. Okay, 50 kilonewtons per meter, and a loss angle of 20 degrees. So delta is 20 degrees. Now I've got an equation. This is from the formula sheet. Tangent of delta is C omega naught divided by K. So delta, or C, sorry, must be K tangent of delta divided by omega naught. Obviously omega naught is root K upon M. We've got K and M, and that comes, if you plug the numbers in, you get 6.32 radians per second. Okay, let's zoom out just a touch. So C, taking this equation, C equals 50 tangent of 20 degrees divided by 6.32. Don't forget to put it in degrees on your calculator, okay? So that's going to be 2.877 times 10 to the 3 Newton seconds per meter. So over here we've got C is 2.877 times 10 to the 3 Newton seconds per meter. So as from before, we've got a base excitation problem. So there's my base, there's my car. So the equation of motion of the mass, okay, we've got m x double dot plus c x minus xb, both dots on top of there, plus k x minus xb equals 0. So if you take Newton's second law of the mass, it's quite clear that we've got the inertia minus the spring minus the damping, okay? And the inertia equals, the sum of all the forces equals mass times acceleration. Obviously the springs and the dampers will always oppose motion, and so they become plus if you move them all to the same side, okay? And obviously what I'm going to do is I'm going to rearrange this equation to put all the x terms on one side and all the xb terms on the other side. I'll make the substitution that x is big X, e j omega t. So that means that x dot is going to be j omega x e j omega t, and x double dot is going to be minus omega squared x e j omega t. I'm going to say that xb, big xb, e j omega t, so xb dot okay. So plugging in the values, I get that equation. The exponential terms will cancel out, and I need to find my output, which is x, divided by my input, xb. Note that h omega also gives the ratio, in this case it's important, of the accelerations, okay? It's the same relationship, okay? So that's what we need to know. So if I enter the equation sheet, we know that the frequency response of the output, okay, the output, so I'm going to call that x double dot omega equals h omega squared s xb double dot omega. So that's the input. That's on your equation sheet. And we know the expected value of x double dot squared, which is what we're looking for, is the integral between minus infinity and infinity of s x double dot omega. So that's going to be the integral minus infinity of I forgot my d omega in that first integral. Apologies. So that line gives the relationship between the input power spectral density, which we've been given, and the output power spectral density, which is what we're looking for. The integral of this will give me my mean square value, okay? And so if I integrate that with respect to frequency, so like I said, there's a d omega in there, I forgot, that equals the integral of this, okay? This is a constant, we've been told, so that can come outside, okay? And then obviously we integrate this here, which is there, and we use our integral identity for that. If in this case, it's quite clear that B naught is going to be K, B1 is going to be C, A naught is K, A1 is C, and A2 is M. And so, if I go through and do the integral, I get S naught plus omega minus omega times by pi I get K squared upon K times by M plus C squared divided by C M. So that equals S naught plus omega minus omega pi Km plus C squared M. So that's my solution, but obviously I need to find a value for S naught. So that's what we've been given in the question, S naught. Wait for you to catch up. It's 0.001 g squared per hertz, and that equals 4 pi S naught in terms of radians per second. So it's quite clear that so if I put this term into this equation, I end up with E hex double dot squared equals 0.001 divided by 4 pi times by pi Km plus C squared divided by Cm G squared. So the pi's cancel, which helps, okay? And so I get We've got k, which is 50 times 10 to the 3, m, which is 1250, plus c squared, which we calculated to be 2.877, divided by cm, which is 2.8. And obviously, if you do the sums using your calculator, you get, oh sorry, there's a g squared over here, 0.0049 g squared. So the root mean square value, x double dot RMS, so the square root of 0.0049 g squared. So, our problem is a car on a road surface, okay? A car with a mass 1250, spring stiffness of 50 kilonewtons per meter, and a loss angle of 20, okay? To calculate C, we use this equation from our equation sheet. So C is k tangent of delta divided by omega naught. Omega naught quite clearly is root k upon m, so that's straightforward. And then so I'll plug in the numbers. Obviously I've got a 50 times 10 to the 3 here, obviously forgot that. 50 times 10 to the 3, that's my k term. Tangent of 20 degrees, don't forget to put your calculator in degrees when you're doing this, and you get 2.877 times 10 to the 3. So there's my c term. It's a mass, so a base excitation problem. So equation of motion looks like this. If I took the free body diagram of m, of my mass, then this is what I get. I put all the x terms on one side and the x b terms on the other side, over here. Make the substitution with an oscillation, so my exponential terms. So I get my x dot, my x double dot, and the same with xb. I get my xb dot. I plug them into the equations, into this equation, I get this situation. The exponentials will cancel, and if I put my output over my input, I get my frequency response function, okay? Complex frequency response. And so there's my relationship, and that's the same relationship if I'm dealing with accelerations, which I am doing in this problem. So we know that the output power spectral density is going to be the input power spectral density multiplied by h omega modulus squared. Okay, if I take the integral of my output, I get my expected, my mean square value. Okay, there's my integral of that. So obviously the integral of the output, so the input times my frequency response function, will also be my mean square value. Now this is a constant, so I take that outside the integral. I do the integral of this between minus infinity and infinity. Using the identity, we know that B0 is K, B1 is C, A0 is K, A1 is C, A2 is M. So I plug them into my solution and I get this times by the input. Okay, so my input times by this. Obviously that's simplified. Now to work out this input in terms of radians per second, I need to convert it from g squared per hertz into g squared per radians per second. And so that relationship is that this equals this. So I take my value here, divided by 4 pi, I get it in terms of radians per second. So then I can plug this term into here, okay, which is what I've done down there. So I plug that term into there, I get 0.001 divided by 4 pi times by pi, okay, km plus c squared over cm times by g squared. And obviously at this point I can then plug in the numbers, which is what I've done here. And so 0.001 divided by 4 is there, the pi's cancel. I've got my k term, my m term, my c squared term, c times by m. Plug that all into a calculator, you should get 0.0049. There's a g squared at the end. And so obviously the root mean square, I take my mean square, I square root it, hence RMS. And so it's the square root of 0.0049 g squared gives me 0.07g. Okay, so that's the solution to that problem.